We've got another amazing live session with none other than Andrew Liu. You might have seen him earlier today.
Yeah, Andrew's going to help us learn even more about how Azure Cosmos DB works under the hood. Andrew, welcome back to the stage.
Cool. Hey, nice to be here. Hey, everyone. We're going to do a bit of an experiment. We're going to do a whiteboarding session, and we're going to go right into this. So, have you ever wondered what happens when you create when you go to the portal, you hit create Cosmos DB, and just what happens behind the hood? That's the intention of this session. And so let's start with our SDK and taking that perspective from this point of the view of the world. So the SDK is going to be embedded either in an application, or even when we build things like the Azure portal, we view that as a client from the database's perspective. So think of this as the app or the portal. This is wrapping our SDK. We actually have multiple flavors of the SDK beyond just programming languages. We have a management SDK as well as a data plane SDK. And what ends up happening is when we do from a client-server perspective, behind the scenes, what this is going to go and talk to is a control plane and a data plane. And we're going to think of these two things as very separate. The control plane is going to be wrapped over ARM. Oops. This stands for Azure Resource Manager. And so whenever you make REST calls over into a DNS that looks something like management.azure.com, what happens behind the scenes is you can think of ARM, one mental model is like a big reverse proxy. And that reverse proxy, when it goes, hey, OK, you want to create a Cosmos DB or add a region or fail over to a different region or scale your RUs, what that's going to do is it's going to go route those requests into what's called a resource provider. And so Cosmos DB has a resource provider, and of course, every other Azure service out there also has its own resource provider. And ARM's job is to go and route to the correct resource provider. Now, on the data plane, this is going to be a different DNS entry. This is going to be cosmos.azure.com. And the data plane is responsible for what you think of a database actually does, right? This is going to be writing your data, indexing it, and then making it available for fast, efficient queries. And so when we go and look at that path, all of these requests will first flow into our front-end server in Cosmos DB. We like to call this our gateway. And the gateway's job is to do request routing, because what happens is we have a distributed backend behind the scenes. And in the back end, what this will map to is effectively big clusters that we run behind the scenes. They are multi-tenant federations or clusters. We like to use those words interchangeably. And within those clusters, this is going to be the deployment model in Cosmos DB. So if we go look from a physical to a logical mapping, on the logical layer, you're making this thing called a database account, down to a database, down to a container. And I might use different words like container or collection interchangeably. Container, we kind of use that as kind of the API agnostic way of saying that. And then depending on some of the Cosmos DB APIs, you might have seen the word collection, especially for any of the document-oriented data models. And within that, we store our data. Everything within this container is what is being powered by the backend on the data plane. And behind the scenes, what this container is it's not a single server, right? Like what we're doing is we're stitching together replica sets. So think of I have a little replica set powered by Service Fabric, where I have a primary and a few different secondaries. And each of these is a database replica. And a database replica is going to be the core building block for what's powering the software behind the scenes. This is going to have the query engine, it's going to have the indexing layer, it's going to have the storage. And beyond just doing the bread and butter of what a database does, it's also going to have other things like admission control, and that's where we're going to have things like our resource governance. So think of this, what we're doing is we take this software, we stitch it together into a replica set. And on that replica set, this is what's going to form a physical partition. And what happens is when you scale a container, we're going to create one or more physical partitions. Each physical partition today is able to support up to 10,000 request units per second worth of bandwidth. It's also able to support up to 50 GB worth of storage. And so when we talk about infinite scale, like millions of RUs, what we're really doing is we're just taking that container and we're sharding it aggressively, where we're creating tons of these different physical partitions behind the scenes. Now, these get placed onto these big federations. So back to from a federation perspective, think of this as in the data center, I have a bunch of racks. Each of these racks are going to have some shared infrastructure, like a top-of-rack network switch. And we can also think of those in terms of helping us compose what will become a set of fault domains or update domains. And so when we set up these federations that go and host all these different database replicas, what we're doing is on these different nodes, think of these nodes as basically spinning up these replicas and having them on standby. And so when you go through the control plane saying, hey, I need to go scale my Cosmos DB, give me some more RUs, behind the scenes, what that resource provider is doing with our control plane is saying, hey, this workload needs to scale, I need some more partitions. Do we have some bindable partitions? Let's go take a look at this federation. We might have a replica stitched together across different fault domains and update domains. And so let's say I have a couple of different nodes here. We're going to stitch together a replica from each one of these into a bindable partition, and we're going to give that partition over to that container. Now, these federations, don't think of as an account as having to live on a single federation. We span across many federations for infinite scale. And why we do that is we decouple the physical and logical layer, and this allows us to always stay current on our hardware. Speaking of the hardware, this is a nice shout out to our sponsor, AMD. We use, especially in the newer generations of our federations, a massive amount of AMD CPUs. Why we love the AMD CPUs is because they're incredibly power efficient. They give really good watts for the unit of compute that we give, as well as that helps us drive the cost down. And as we drive the cost down, this is what we're also able to go and turn that into cost savings for our users like you in the form of new features. So things like the dynamic auto scale, the RU pooling with the new Cosmos DB fleets, the Cosmos DB serverless. Those effectively what we're doing is we're using elasticity for the TCO of operating a database, right? Every workload is going to be bursty. Any transactional workload is like that. And what we're doing is we're passing all of the savings we get from the AMD into nice elastic features for our users. Now, on the federation, as we go and stitch together these replicas, we can jump into our first, I think, bigger, meatier topic. And that is going to be how we look at the partitioning. So Cosmos DB uses a technique called consistent hashing. It's a fairly ubiquitous concept for any kind of sharded database. It tends to be the industry standard. And I'll kind of walk through that in terms a little bit just to help understand it and compare it to what maybe folks will think of as like a naive hash. So in a naive hash, think of it as I'm going to go partition my data, and behind the scenes, that container now has a ton of these physical partitions, right? Like a container has let's say 50,000 RUs. We know each one can support 10K each. So this is going to go and create 5 of these physical partitions behind the scenes. It's going to go then route, let's say, some data onto this node, some data over into this, or this physical partition, this physical partition. How does it know and to deterministically route, right? Like if I go and query for, let's say, Alice's data, in a user-based system, I need to be able to actually hit the partition hosting Alice's data. Otherwise, when I do that query, I'm not going to find anything, right? And so what happens is we ask Q for a partition key. And so let's put in some values here just to give you an idea of what is happening. So we have a logical partition key. This is the partition key that you're supplying. And that's going to go hash to some numeric value behind the scenes, right? We can use different hashing algorithms. In this case, Cosmos DB uses this algorithm called murmur hash because it's very compute efficient. And let's look what happens if you do a naive hash, right? Like in a naive approach, let's say if I only had 2 partitions, the challenge you're going to run into in a naive hash is if I, let's say, go and let's say mod 2, well, what I'm going to see is a distribution that looks like 1, 2, 1, 2, 1, 2. Now, what happens if I need to grow that on an elastic workload, I'm scaling that over to 3 partitions. And right away, you're going to go see what the problem is and why a consistent hash is so valuable. So when I do a mod 3, right, I'm going to get a distribution that looks a little bit more like 1, 2, 3, 1, 2, 3. And notice what's happening here. If I am mapping data, let's say Alice, Bob, Carol, let's see, put Danny, Eve, etc. Notice this challenge where if Danny mapped to partition 2 when we mod 2, but now maps to partition 1, we're doing effectively a huge shuffle, right? A lot of data would have to go from the second partition into the first, from the first into the second, from the first into the third, the second to the third. That's not very efficient, right? And so this is why a consistent hashing scheme is a much better way of doing this rather than a naive hash. But this will give you the intuition in terms of how this works out. So a consistent hash you can think of as a range partitioning on top of a hashed-based scheme. So if I go and think about the hash values, where this is the min value on a number line, and I do this as a circle, since everything is going to go map onto this ring. If I look at min value on where it hashes to 0, 0, 0 to FFFF, if I have 2 partitions on day 1, then the way of scaling this is actually very easy on mapping. What we can do is we can just go chop the number line, right? And so from 0 to approximately half, and then from half to, let's say, +1 over to max value, I can go map this into physical partition 1, and this can go map to physical partition 2. Now, what's neat here is in a consistent hash, rather than doing any of this shuffling, what happens if the first partition is filling up? Or what happens if the second partition is filling up? Well, then we can go and dynamically allocate more partitions by splitting them. And so what happens is, let's say I need to do a split where I need to go and map now a third partition. So we can go from 0 to, let's say, quarter, and then quarter to quarter +1 over to half. Well, notice that I can now relocate, let's say, or not even relocate any data. I can just go and on the hash values, directly if like Alice was here, Bob was here, and Carol was here, rather than having to shuffle things around, I can just say, hey, Alice and Bob used to be co-located on partition 1, but partition 1 has now turned into partition 1, let's say prime, and partition 1 double prime. And all we've done is split that data. And what's awesome about this is Cosmos DB can do this as an online operation where we'll handle the splitting or merging of the data on allocating the partitions, and then dynamically cut over whenever you need to go and perform one of these operations. So what Cosmos DB does is really the runtime aspects of partitioning so that you have auto partitioning. And really, as a user, what you're left with is the design time aspect, which is choosing a good partition key. And this is why it's so important to choose a good partition key, because ultimately, if you're partitioning, let's say, by a user ID, then what we're doing is we're using that user ID to go deterministically route which piece of data, let's say Alice's piece of data into partition 1 prime, Bob's data into partition 1 double prime, and Carol into partition 2. Now, this is one aspect of scale out. This is the partitioning aspect. The other thing I'd like to cover is the replication side. And what replication is really there for is a little bit different, right? Partitioning is what gets you ability to scale your request traffic. In particular, it does really well at scaling your write traffic. It can also scale your read traffic, right? If I have millions of QPS, well, I cannot have an infinitely number of CPU on a single box, on a single VM. There's still the physical aspect of it. We just put you on more computers. And so what we're doing is we can power many, many CPUs as long as we divide that data set and partition it out. Now, what replication is doing a little bit different is copying that data. Copying that data gives us two different things. One that's similar and one that's very different. The similar thing is going to be, it's one way of scaling your read throughput. The other thing that it can do is it gives you a lot of redundancy. And this is how Cosmos DB gives you 5 nines of availability. And we can think of this in multiple grains. So let me go and get some board real estate. And on the replication side, when we zoom in on any of these partitions, remember what we have is a replica set. And what we're doing is we're using a concept called quorums, or quorum replication, to go and provide that availability. Now, how we do those replica sets is going to be a little bit different in terms of within a region versus across region. When you do across regions, what we're effectively doing is we're spawning another partition in each of the different regions. And then what happens is we can have multi-write regions. What happens is one of these secondaries will get designated as a forwarder. We might have 3, we might have 4. This is a bit black boxed, but what we do is we dynamically size a quorum across a replica set, and this can be in, let's say, region 2. This can be in region 1. And within a region, we rely on Service Fabric heavily to do the within a region replication. And what's beautiful about this is it handles a lot of the things like leader replication for us. Let's say a primary is going down, whether it's willingly, intentionally. Let's say we're deploying a database software update. Have you noticed like Cosmos DB doesn't really have maintenance periods? It's just always online. You've never seen us say like, hey, it's time for a Windows update or it's time for an application update. That's because behind the scenes, what we're doing is we're just dynamically changing, oh, okay, let me take down a replica that's on a different update domain or a different fault domain, and let me designate and promote one of these secondaries over to a primary, and then shift that traffic over. What we're doing is we're live doing rolling updates, and that way when this replica is brought back online, what we can do is we're just dynamically writing to a rolling set of replicas behind that replica set. Now, what a quorum is a little bit different from your traditional primary versus secondary replication. In a traditional database, like let's say a relational database, what you're typically working with is either synchronous or asynchronous replication. And those come with pretty steep trade-offs, right? Like when you do synchronous replication, if your goal was high availability, if the primary goes down, that's fine. You can go and fail over to a secondary. But it actually goes and has some risks as well. What if the instead of the first failing, it's the second one that went down, right? Well, if you're synchronously replicating, well, even if the primary is healthy, now I have to go and cut that secondary in order to restore work back onto, bring the right availability back. And so what synchronous replication is doing is it's giving you really strong consistency. And in terms of disaster recovery terms, what you're really prioritizing is a low recovery point objective, right? Like if I go from the primary to the secondary, since everything was synchronously replicated, if I wrote to the primary, I know it's in the secondary, so I have a recovery point objective of effectively 0. Now, where synchronous replication is really bad at is the recovery time objective. If you are having to coordinate a failover, failovers take time, and so this is where you're going to be less happy as opposed to more happy. And then asynchronous is the exact opposite, right? In an asynchronous model, what you're going to see is your recovery time objectives. Well, hey, if the secondary fails, that's fine. I can just keep serving out of the primary. I'll just let the secondary lag behind. But how far is it lagging behind? If I do a cutover to the secondary, is the data that I just wrote even there? And so what you're going to see is the recovery point objective is going to be, well, it's an eventually consistent model, so you're going to have a lack of consistency, but you're trading up the recovery time objective. Now, where quorum replication innovates on this is rather than thinking of the world as, hey, let me just have one additional redundant copy or n number of redundant copies where I have a primary secondary model, what I can do is I can always write to a quorum of replicas. So imagine that if I have 4 replicas here, a majority quorum would be something like writing to at least 3 out of 4 of those replicas. That means that if any replica were to fail, in this example, let's say this 4th replica bombed out, and I was able to write to the primary and to these secondaries, or even if that primary dies, we go and promote one of the other replicas to be the new primary, and we get 3 out of 4 on the new topology. Any node can fail, and we're able to maintain that availability. Now, on the read side, this is what is really interesting, is if I go and circle any 2 replicas, right, I can do a minority quorum. Well, because I'm allowing fault tolerance for any replica to go down on the write path, on the read path, as long as I read at least 2 different replicas, I can still guarantee strong consistency even though this is in a fault-tolerant system where I allow a replica to go down, right? Like, I'm always going to have replica overlap. If replica D goes down, well, A and B will, of course, both have the data. B and C would both have the data. C and D, the D would miss, but the C would still, because it's further forward in time, it's always going to win that vote, that you're able to get strongly consistent reads in the midst of a downed replica. Now, that's what we're doing within a region. And then across regions, what we do is we designate one of these secondary replicas to go and replicate over to another region. There's some slight caveats to that, depending on whether you're using strong consistency versus any of the other Cosmos DB consistency levels. If you're using any of the weaker consistency levels, you can think of it as we're doing an asynchronous replication over to the secondary region, and this is what gives you, higher availability, faster RTOs, at the trade-off of consistency. Or if you're using global strong consistency, what we're doing is you can think of it as synchronously writing to multiple regions. Now, there's a bunch of more things that go into that. For example, we can do dynamic quorums where if we have a third region, we can vote 2 out of 3 regions to give you even strong consistency that allows a region to go down. And what's really cool is Cosmos DB allows, it's not a single primary system. We're able to put primaries in each of these 2 different regions. And so on the SDK side, you never have to really wait for a failover. If you're in any of the weaker consistency levels using multi-region writes, if I'm writing to region 1 and region 1 goes down, that's fine. The SDK is actually smart enough. When you set in the, when you instantiate the SDK, you have that connection policy. You can set what the preferred location is. What it's doing is it's going to do a live redirection to the secondary region without even waiting for a server-side failover. And this is how you can collapse that recovery time objective down to 0. And with even in a strong consistency manner, we're able to go and minimize the RTO, where we now have the ability of doing fast failovers in a strongly consistent setup. We are very happy about, recently we had launched per partition automatic failover. What it does is, rather than looking at, hey, if one partition's unhealthy, another partition is healthy, and trying to have a live ops team go, hey, should I fail over, should I not fail over? That tends to be the bottleneck for any failover. We don't have to go and do any decision making. In a strongly consistent system with PPAF, what we can do is we can also then trigger that one partition to independently trigger a failover in this big distributed database without having to impact all of the other healthy partitions. And so this is how we're able to go and try to give you just softer trade-offs rather than thinking of the world as extremes in terms of eventual or strongly consistent systems with like, hey, do I want RTO or RPO? You can get both by using quorum topologies for replication, and then doing a lot of magic around redirections. Now, a third thing I want to go and show you that I think is good for every developer to understand in Cosmos DB is the resource governance aspect, right? Like when you go and create a Cosmos DB container, you're going to see like, hey, what is this thing, request units? This is what allows us to go and do pay-per-request models around serverless. It's what allows us to give you guaranteed throughput. Rather than just best effort, hey, we have some nodes with some cores, we're able to give you predictable performance. And so what happens is each of those replicas, when I look at the replica, where behind the scenes you can think of it as we have a resource governor, and you can think of that as like a token bucket algorithm, right? If you haven't seen token bucket algorithm before, think of it as like a bucket of tokens, and the request units are those tokens. When you go and do a database read, a 1 KB read is actually the baseline charge. That's one request unit. What we'll do is we'll take a token out of the bucket, right? So we'll subtract one request unit. And then on the resource governor, in order to go and say, hey, is the system overloaded? Is it not overloaded? We want to give predictable latency. So let's try to avoid anything like overly saturated CPU. What we'll do is we'll govern that based off of the relative CPU memory and IO footprint of that request. And so each second, what we're doing is that we're then replenishing those tokens back in on a timer interval. And as long as I have greater than 0 RUs, we're able to keep serving requests. Now, one innovation that we had that's a bit new is the RU pooling functionality that we did with the Cosmos DB fleets. So what happens is we have one of these token bucket resource governors on each individual replica. So on that partition, right, so I have a partition, the RUs right now, first is a shared nothing counter. We have this on each individual replica. This is now a partition, and then we go and divide that evenly across partitions. What happens if I have a hotter partition and then I have like, let's say a colder partition? Can we go and donate budget from a colder partition over to a hot partition in a responsible manner? And so that's what the RU pooling is all about. We're able to pool across different accounts up to, we have also a node level governor. But on the local governor, what's happening is, historically, if we just use a shared nothing counter, we have a few different trade-offs, right? The benefit of having a shared nothing counter is, let's say if one node goes down, it's not a global rate limiter. I can go and continue to serve requests, and the system is highly resilient. But the trade-off here is, well, what happens if I'm overly spread thin across many replicas, many partitions, is all of these now also report into we call a global rate limiter, or we internally like to call it a controller service. And so think of it as a heartbeat where it's not on the critical path, where each of the local replicas is going and saying, hey, here's my utilization on how many RUs I am consuming, and here's the leftover budget that I have. All of that leftover budget is then sent over to the global rate limiter, where the global rate limiter on the response can also go heartbeat back saying, hey, you just used all of these RUs, and you have some leftover budget. Meanwhile, this other partition's running hot, but because we have leftover budget somewhere else, let's say if this is the one that's running blazing hot, and this one's got leftover budget. What we're able to do is the global rate limiter can say, hey, let's relax some limits. I can give and donate some RUs back over to the other partition and help you pool that. And so these are some of the really cool new capabilities where we can give you leftover budget, give you higher burst ability, and do so in a responsible manner that still preserves a shared nothing architecture on the front door. Now, this is a lot to take in. Let me go and zoom out. We talked a little bit on partitioning, on replication, and on request units, on what happens behind the scenes in Cosmos DB. Let us know what you think about this format. If this works out for you, there's a lot of other topics we can do in the future, like indexing, the query engine, et cetera. Let us know in the comments on what you think, and please do fill out our form evaluations. Otherwise, thank you so much.
Thank you so much.
Thank you, Andrew. You know what's crazy is that that was such a great behind-the-scenes look. And you gave me something like this, I think maybe the first day I started on the team. So it's always great to kind of see this again. It's a refresher. Keeps me really up to speed on what we're doing.
Oh, yeah. I mean, I figure we keep doing this as an onboarding thing internally, but honestly, it helps our developers so much when they know what's happening behind the scenes too, on rationalizing, hey, why is the system behaving the way it is? And that's the intent of also disclosing this out broadly here.
Fantastic.